So we've seen the concentration time equations for zero, first, and second order reactions. Let's talk a little bit more about the half-life equations of those reactions. So first order, the concentration time equation was ln of R at time t equals negative KT plus the ln of R at time 0. That's reactant concentration at some time versus the reactant concentration initial. If we're talking about half-life, that's the amount of time it takes for the reactant initial to be cut by half. So half-life is when initial reactant concentration is half of what it used to be. It's related to, it's not equal to that. That's what I'm saying, kind of, sort of. Yeah. So if we substitute in ln of 1/2 R0 equals negative KT, and now I'm solving for the half-life, so I'm just going to substitute in T1/2 for that thing. Oops, R0. I can rearrange and make it ln of 1/2 R0 minus ln of R0 equals negative KT 1/2. When you subtract ln's, that's the same thing as dividing them. ln of 1/2 R0 divided by R0 equals negative KT 1/2. And I can absolutely cancel out R0 divided by R0. Keep up. Hold on. We're making it. That's ln of 1/2 equals negative KT 1/2. And this part you might not remember, but 1/2 is the same thing as 2 to the negative 1. So ln of 2 to the negative 1 equals negative KT 1/2. And why I would do that is I can pull my negative out front. So we're going to flip over to say negative ln of 2 equals negative KT 1/2. One final solving, and we get T 1/2 equals ln of 2 over K. So if you ever plug in ln of 2, you'll see that ln of 2 is 0.693 over K. So you might see the half-life equation for a first-order reaction written either of these ways. That's first order. Up next, second order. Lather, rinse, repeat. Second order equation. Concentration time is 1 over R at time t. I'm going to go ahead and put it in this formatting. Minus 1 over R at time 0 equals positive KT. So the half-life is the time when RT is 1/2 of the original. So 1 over 1/2 R0 minus 1 over R0 equals positive KT. 1 over 1/2 equals 2 over R0 minus 1 over R0 equals positive KT. And since they've got the same denominator, 1 over R0 equals KT, and I should be substituting in T 1/2 all along here. And finally, divide 1 over K times R0 equals T 1/2. That one's much simpler to solve because we don't have that ln stuff that you guys don't remember. So that's the half-life equation for a second-order reaction. Do you have to memorize these equations? No, you can actually substitute in to figure out what the equation should be. Or often what happens is you'll be given some half-life equations, but you're not told which order it is, whether it's 0, 1, or 2, 0 first or second order, and you'll just have to recognize which is which. All right, time for the 0th order. The 0th order equation was RT minus R0. We've seen it in other formatting. Equals negative KT. The half-life is when RT is equal to half of R0. So half of R0 minus R0 equals negative KT 1/2. 1/2 R0 minus 1 R0 makes negative 1/2 R0 equals negative KT 1/2. T 1/2 equals R0 over 2K if you simplify, because you're dividing by negative K, your negatives cancel out. This is the half-life equation for a zero-order reaction. That's first, that's second, that's zero-order half-life equations. All you do is substitute in half of the initial concentration for your half-life thing, or you memorize equations, or you recognize equations, whatever, up to you. I hate memorizing, but you do you. So in all of those concentration time equations, no matter the order of the reaction, we were only able to calculate reactant concentration, not product concentration. How do we calculate product concentration? Well, we can organize ourselves in a table the way we've been doing all semester. So if you know the initial and the change and the final, like a limiting reactant kind of way, if you know initial concentration of reactant and final concentration of reactant, you can use your values for reactant to determine the value of product. Put in variable terms, let's click through. If I know the initial pressure of N2O4 gas is a certain amount, I'm going to lose some, I'm going to gain some. Yeah, there's no product, sorry. I'm going to lose some reactant and gain 2x product. Remember that coefficient matters. So my final concentration is going to be initial minus x, but my final product is just going to be 2x. So how do I use this to calculate what this should be? Using a concentration time equation, I can find the concentration final, the reactant's concentration at time t. This is a first order reaction that has been solved for this and this alone. The ln's have been taken out. That's why this exponential e is here. But I can solve for this value. Knowing initial and final, I can find x, and then I can plug in 2x to find my product concentration. What do we do with all these formulas that we have? Well, we can do problems like this. For the decomposition of N2O5, the rate constant is this. If the pressure in the container is 800 milliliters of mercury, what's the pressure in the container after 200 seconds? Where do we start? Well, we have different concentration time equations for different ordered reactions. So we need to know the order of this reaction before we can do anything. Any idea what order it is? Because of the units on the rate constant, we can know that this is a first order reaction. Yep. It does not have to explicitly tell us it's first order. We look at the units on the rate constant and we know that those are the units for a first order reaction. So, to find the pressure of N2O5, we have an equation to do that at 200 seconds. Because it's a first order reaction, we're going to use the Ln version. So we cannot calculate NO2 or O2 here, but we can find the pressure of N2O5 at 200 seconds. So that would be the Ln of the pressure of N2O5 at 200 seconds. We don't know. That's what that one is. Equals negative 0.007. My circle is in the way. Negative K times T, 200 seconds. Make sure your timing stuff cancels out. Plus the Ln of 800 millimeters of mercury. So whatever units are in this Ln, that's what units this Ln are going to end up in. So I do that math, and I get the Ln of P2O5, no, of N2O5, equals 5.284. And I each of both sides of that thing, and I get the pressure of N2O5 at 200 seconds is equal to 197.3 millimeters of mercury. Now what? I'm going to use a limiting reactant table to find out what my pressure of everything is, because my question is asking what's the pressure in the container. So that's all gases, and my equation actually doesn't have all the states of matter there, but it should, and they're all gases. Nope, that's a 4, 4, 4. And O2 plus O2. My limiting reactant table looks like this. My initial concentration of N2O5, my initial pressure of N2O5 is 800 millimeters of mercury minus 2x, and my final is 197.3. I have none of this, none of that. I'm going to gain 4x, gain x. I use this thing to solve for x. 800 minus 2x equals 197.3. X equals, where are my notes? 301.5. So once I find my x, 4 times 301.5 is 1206, and 301.5 itself. But my question, remember, is what is the pressure in the container? So that's asking for P total. So I take my final row and I sum it, and the sum of my final row is 170.4.5 millimeters of mercury. So all we needed was the concentration time equation for a first order reaction to find the reactant concentration after 200 seconds. Then we just did a regular limiting reactant table to find our total pressure after 200 seconds. All right, that's it.